questions. It's not the whole question, as you can probably imagine. It's just part A, and theoretically, of course, this is related to what Luke was talking about yesterday. So I'm just going to get to my overhead projector here. We'll walk through this problem together. So Robin works as a server in a small restaurant where she can earn tip money, extra money, from each customer she serves. So I, you've heard me say it. We're setting the table here. We're just setting the tone. We try and understand that students, English may not be your primary language, your first language. So any words that are not very common, we try and define those. And so we want everyone to have sort of an equal footing on this. The histogram below shows the distribution of her 60 tip amounts for one day of work. So I would spend, a minute or so just sort of, really understanding the problem and equally important understanding the graph down here. Now, with 60 data points, there's no way we want you to type that into your calculator. So I think that would be the wrong approach here. And when I really look at this histogram here, I guess I know that between $0 and I guess that's $2.50 here, right? And $7.50. There were 25 tips over that interval, but I really don't know what each one of those 25 were. Were they all $1? I don't know. Were some $1, some $1.50. So I think typing these in would not really be helpful here, and it would be a huge time constraint that we wouldn't want you to do. So looks like there's 25 from 0 to 250, 22 from 250 to 5, etc. I might really quick add those up and I get my 60 tip amounts. So part A, very typical. We've seen this a lot on previous AP exams. Write a few sentences to describe the distribution of tip amounts for the day. So I want distribution and tip amounts. You can underline keywords. You can do pretty much whatever you want. It's your exam. So I'm sure you've all heard shape, center, spread. I think our books do a really good job with that. And I can remember a former reader, a friend of mine saying, the kids are good with this. They're very robotic. They know how to do this. I've expanded on that in my classroom just a little bit. We call it GSOCs. And so the S is still shape, that's still center, and that's still spread. But the G stands for, are there gaps? Are there holes in the data? And clearly there is a gap here for some reason. And of course the O is the outliers. So again, scoring guidelines in the past have traditionally asked for a shape, center, spread. Just from a good statistical analysis point of view, I do think if there's gaps or holes in my data, that's important and I need to address that. If there's any outliers, I want to address that. So let's do shape first. The distribution of Robin's tips are skewed to the right. So I've actually done two things here. Sorry about that. I've actually done two things here. I've talked about the shape. It's clearly skewed to the right. And I've also gotten sort of tips and Robin. And so I have context. And that was strategic. I wanted to get that in, one sentence and maybe, get two things at once. There is a gap in the tips from $15 to $20. And the one tip amount from 20 to 22.50 could be an outlier. So I guess in my little acronym here, I've addressed the G and the O, right? The gaps and the outliers. And many times I try and do them together. For some reason, there were no tips in this sort of interval right there. I don't know why. And there's one tip here. Again, that could be $20, it could be $22.50 or anywhere in between. I don't know. Again, I don't want to type all those numbers in. I don't even know if I could type them all in here. So I don't want to sort of definitively say it's definitely an outlier or it definitely isn't. Um, I've addressed both of them, and it could be an outlier and it could not. And so I'm going to keep moving on. So I've talked about gaps. I've talked about shape. I've talked about my outliers, center. I'm going to go median here. Again, I don't really know if I can even calculate the mean. So I'm going to say the median tip amount. So it's somewhere around 30, right? So 25, it's in this second bin here, right? So the median tip amount is between $2.50 and $5, something like that. That's all I need to know. It's in the second bar here, the second interval. And again, I don't know exactly where it is, and we didn't want students to do that. And so let's talk about spread. The tips vary from 0 to 250 to 20 to 2250. And that's one way to talk about the spread of the data. Again, I don't know exactly where those 25 tips lined up from 0 to 250, and I get it, I don't know that, but I've somehow talked about the spread of my data. So that's it. That's part A. Again, most scoring guidelines in the past have required that students talk about shape, center, spread. I checked the scoring guideline this morning, and of course, we wanted shape, center, spread. We also wanted some context here. So we needed you to talk about Robin's tips or tip money or something like that. And I think I've got that in. And gaps and outliers, to me, they're just super important, and we need to talk about them. So I got those in. And as we get closer and closer to the AP stats exam, Luke and I are going to talk a little bit more about how we score the exams. And there's one day where I'm going to ask you guys to become AP readers, and we're actually going to score some student papers. We wanted students to address 4 of those 5. So shape, center, spread, context, Robin's tips, and gaps and or outliers, either one of the 2. And if you had 4 of those 5, you got what we would call an E, essentially correct, and that's, you know, you're well on your way to starting out the exam on a good note. So that was the homework from last night, and I'm sure Luke did a great job. So let's go back to what we're doing today. I'm going to do standardizing scores, or Z-scores. The Z-score is a standardized score. So real quick, you can find some updated information on the AP stats testing, and hopefully more is coming. Well, Luke and I will give you everything we know as soon as we know it. The last link here will actually get you to the schedule of all of our events for the next 3 weeks. And so hopefully you can kind of make a plan as to what sessions you want to watch and which ones you don't need to. So I'm in topic 110. Again, this is really more for the teachers than you guys, but we're talking about standardizing scores. So one example of a standardized score is a Z-score, which is calculated as your Z-score equals XI, your individual score, minus mu, your mean, over sigma, some standard deviation. A Z-score measures how many standard deviations a data value is from the mean. You can be positive or negative. You can be 3 standard deviations above the mean, or theoretically minus 5 standard deviations below the mean. So that's all it is. We can always calculate a Z-score if we have those three inputs, your score, the mean, and a standard deviation. But we can only read a Z table, or we can only use the percentages, percentiles from a Z table if our data is at least approximately normally distributed. And so when we did inference, you know, the first couple of weeks, you know, we really needed to check that condition. And I always like to say to my students, there's no data set in the real world that's 100% perfectly normal. So we shoot for, you know, approximately normally distributed or something like that. The standardized test statistic, this white box here is right from your formula sheet that you'll have on the AP stats exam. And so some sample statistic, that would be my XI, minus some parameter mu, over standard error of the statistic. And so earlier in the year, we were just using, whatever our standard deviation was, and we didn't really worry about sample size. And as we got into inference, of course, the sample size started to make a bigger input. And so I like to call that the standard error is the standard deviation based upon my sample size. And bigger sample size is always better, excuse me. Okay, so I found a couple of multiple choice questions. And we'll start out with those, and then we'll go to a free response or two if we have time. So the lengths of individual shellfish in a population of 10,000 shellfish are approximately normally distributed with a mean of 10 centimeters and a standard deviation of 2 centimeters. So there's a lot of good information in that. I know what the mean is, I know what the standard deviation is, and I have a pretty big, I guess, population here of 10,000. Which of the following is the shortest interval? And boy, that's such a key word right there. Which of the following is the shortest interval that contains approximately 4,000 shellfish lengths? So I'm going to go back to my overhead projector. So there's the same problem right here. So I clearly would have underlined shortest interval, and that's so key here. I like to give this problem to my students pretty much every year, and a lot of them, I like to say, swing and miss. They get the wrong answer because they sort of overlook that. So anytime I'm talking about standardized scores or Z-scores, and I've been drawing some terrible normal curves here. I don't know why. I think I'm used to standing at a board, not writing on a piece of paper sitting down. I like to sketch a normal curve. I have these 3 rows here. And this first row is always what I call sort of my raw data. This is going to be, height in inches, something like that, okay? My second row is always my Z-scores. And my third row is the area under the curve, my percentile, my probability. At different times of the year, sometimes I'm using area, sometimes I want percentile, and sometimes I want probability. So you'll see me kind of draw a normal curve, or at least attempt to draw a normal curve. It's a pretty bad normal curve. And I always have these 3 rows, and I always sort of start out the same way. And there's a lot of numbers on a lot of these problems, and I think it just sort of helps my kids get into the problem, and it helps them kind of line things up, I guess. So you can see that I did that on this problem here. So I tried to draw a normal curve. Again, it's really a bad normal curve, but we don't penalize for that on the AP Stats exam. So my first row is my length in centimeters. So it said that the average length was 10 centimeters. Second row is Z-score. Third row, area, probability, or percentile. I see all 3 of those as really the same thing. Again, at different times during the course, I may use area more, I may use probability, or I may use percentile, but I really see those all as the same thing. I tend to always sort of draw in 1 standard deviation above the mean and 1 standard deviation below the mean. For you calculus guys out there, that always falls at your point of inflection where your second derivative is equal to 0, above and beyond the scope of this course, but if you're into calculus, it's kind of a fun little second derivative. So if I add 0.2, I get up to 10.2, and if I subtract 1 standard deviation, I get to 9.8. Well, I know at the mean, my Z-score is 0, and I know I'm at the 50th percentile, and so that just sort of gives me a starting point. If I add 1 standard deviation, my new length is 10.2 centimeters. I'm 1 standard deviation above the mean, and I'm in the 84th percentile, or roughly. And again, if I subtract 0.2 or 1 standard deviation, I'm at 9.8 centimeters. I'm negative 1 standard deviation or 1 standard deviation below the mean. And I'm around the 15th or 16th percentile. You'll see me do this on every problem, and it really helps my students sort of get into the problem. So this problem specifically asked for the shortest interval. And so hopefully logic dictates that it's probably going to be centered around the mean. And I'm just eyeballing here. I'm just eyeballing. hopefully that's around 40% of my 10,000 shellfish. So if you understand or see that logic, well, it can't be A because that's not centered at the mean 10. It can't be B, that's not centered at the mean 10. Sort of feels like that one might be centered at 10, so that's okay. And it feels like this one might be centered at 10, so I don't think I can throw that one out. And this one here, I don't know if that's centered. So I was able to get rid of two of them right away. Well, if I add one standard deviation above and below the mean, that would be what, 68% of my data from the empirical rule, or about 68%. So I know I don't want to go out quite so far to 10.2, and I don't need to go down to 9.8. And so I think I eliminated C because those values were on either side of those. And so now it was really just between those two. And I don't think E is centered perfectly, but let's go to the calculator and see if D makes sense. I want to see if I can type that into my calculator. And I'm looking for around 40% here. Just because I've done this problem a number of times with my students, I think 3 of those 5 answers, if you were to type those into your calculator, get you 40%. So 40% is really not the most important thing here. It's the smallest interval. So I want to go down to normal CDF, normal cumulative distribution function. And I want to start at 9.895. I want to go up to 10.105. The mean is 10. We knew that. That was good. Standard deviation, I think we said, was 0.2. Go back to my home screen. And there's my 40%. So the answer for that one was D. And if I was able to sort of understand conceptually what was going on, I was able to eliminate a couple of answers relatively quickly. I was able to get rid of A, B, and C without doing a whole lot of math or without doing a whole lot of work. E doesn't work either. The correct answer is D. But if you just literally went back to the calculator and typed that interval, I think it gives you 40%. I think if you type that interval, it gives you 40%. But that's not answering the question. The question that I wanted was the shortest interval. And so that had to be centered around the mean. So really nice problem. I give it to my students every year. And I like the fact that there's some sort of strong distractors, get you to the 40%, but not the shortest interval. So here's another multiple choice, and then we'll do a free response. This is from the 2007 exam. So the distributions of diameters of a particular variety of oranges approximately normally distributed with a standard deviation of 0.3. So that's a good sentence, and there's some good information there that I'm gonna go ahead and put down in my little picture soon. How does the diameter of an orange at the 67th percentile compare with the mean diameter? Okay. So you can see I've drawn my normal curve here. Well, I've attempted to draw a normal curve. It's not very good, but that's okay. The first row here is my diameter, but unfortunately there's nothing up here in the stem that's allowing me to plug a number in. You know, I can't type in 10 centimeters or 2 feet or something. I don't know. So I had to leave that blank, unfortunately. There's my mean. My second row is always a Z-score. My third row is always area, probability, or percentile. So I'm consistent. I teach it that way. Hopefully my students are pretty good. It just helps them sort of get into the problem. So I don't know what the mean is, but I know at the mean my Z-score is 0, and I know I'm at the 50th percentile. So that's good to know, and I could fill that in real quick. Again, I like to typically draw in 1 standard deviation above the mean, so a Z-score of 1. I know that's in the 84th percentile, so that's good. And I went 1 standard deviation below the mean, or -1, and I know that that's 0.1864. And I do know that one standard deviation is 0.3 inch. I do know that. Well, they wanted me to compare the diameter to 67th percentile. So again, there's a lot of numbers floating around here. And, you know, my students at times get confused as to what number goes where, Mr. Murphy. So 67th percentile, I typed that into this third row here. I went to my calculator and did, I think, inverse norm. And so if you're at the 67th percentile, your z-score is 0.44, or your 0.44 standard deviations above the mean. And that was pretty important. That pretty much opened up the problem for me. So down here, I just set up a simple proportion. I said, well, I know that one standard deviation is 0.3 inches. So 0.44 standard deviations is how many inches? I cross multiplied, did a little math, and I got 0.132 inches. So if you're at the 67th percentile, your z-score is 0.44, and you're 0.132 inches greater than the mean, and I still have no idea what that number is. So that's a nice little problem. It scored actually lower this year in 2007, this multiple choice. Only 42% of the kids who took the exam that year got this problem right. So I think what makes this a little bit trickier for kids is that, you know, we didn't give you the diameter. We didn't give you what the mean was. In many problems we do. So putting these three rows here really seems to help my kids just get into the problems, and there's lots of numbers around. And I do every problem like this on the board, and I think after a while they sort of just get into the habit of doing that as well. So let's go back and we'll take a look at a free response here. So we've done that one. We've done that one. This is another good problem here, 2012, number 7, but for the sake of time, we'll move on. So here's a good free response from the 2003 exam. We'll do parts A and B. Part C, I think, is a binomial probability, and Luke's doing that next week, I think. But anyways, men's shirt sizes are determined by their neck sizes. Okay, we're just setting the stage. Suppose that men's neck sizes are approximately normally distributed with a mean of 15.7 and a standard deviation of 0.7. So that's good to know. I know the average neck size. I know the standard deviation, so that's good. A retailer sells men's shirts in size small, medium, large, XL, where the shirt size are identified in the table below. So they give me some numerical values for each of those 4 sizes. I know it's really hard to tell by watching me, but I'm 6'6" and about 215, 220 pounds. So I'm a big guy. I'm tall and thin, and I can buy basically no clothing off the rack. Just nothing fits me. So if you ever meet me, or if you know anyone who knows me, they'll say, yeah, he's a big guy. And all of my clothing is long and tall. So I'm probably going to be in the XL, but it might not fit. I might have to go tall. Anyways, nothing to do with the problem. Part A, because the retailer only stocks the sizes listed above, what proportion of customers will find that the retailer does not carry any shirts in their sizes? Yep, that could be me. That could be me. So if I'm making shirts, I would love to sell them to 100% of the population. I would love to sell to every single person alive. Well, we know there's going to be some really tall people and some really short people and whatever, people with big necks and small necks. So the manufacturer probably can't sell to everyone, but they'd love that to be 99, 99 and a half, 99.8 or something percent of the population. They would love that number as close to 100% as possible. And so that's probably what we're going to see, is a number that's pretty close to 100%. They would love to sell shirts to me, people like me. Whether that happens or not, who knows? In part B, using a sketch of a normal curve, illustrate the proportion of men's whose shirt size is medium. Well, we have some numbers for medium. So medium is between 15 and 16. So we'll be able to sketch that, I think, pretty quickly. And then calculate this proportion. Again, we'll skip part C. I think that's a binomial probability, and we'll let Luke do that one of these sessions coming up when we do probability. Okay, so here's the same problem. And you can see, as always, I've attempted to draw a normal curve, and I haven't done a very good job. There are my 3 rows, as always. That's my neck size. We know that 15.7 is the mean, or average neck size. That's good to know. Here's my Z-score. And my 3rd row is area, percentile, or probability. Again, I really see those 3 as really the same thing. Depending upon where we are in the course, I may use one word over the other, but I really see those as the same thing. So if your neck size was 15.7, you're at the mean. Your Z-score is 0. You're in the 50th percentile. Again, I like to add 1 standard deviation above and below the mean. So if your neck size is 16.4, your Z-score is 1, you're 1 standard deviation above the mean, and you're in the 84th percentile. If I subtract 1 standard deviation from the mean, your neck size is 15. My Z-score is -1 or 1 standard deviation below the mean, and I'm around the 16th percentile. Again, it just gets me into the problem, sets it up, and allows me to hopefully answer it correctly. So up here, I want, what's the probability that your Z-score is less than, here's my lowest neck size or smallest neck size, 14 minus 15.7 over 0.7. So it feels like 14 is going to be way down here, right? You have to go another standard deviation and a little bit. So more than 2 standard deviations below the mean. So it feels like it's going to be a small percentage of males out there whose neck size is smaller than 14. Similarly, what's the probability that my Z-score is greater than my largest side, 18 minus 15.7 over 0.7. Again, that's over, I think, almost 3 standard deviations above the mean. So it's way, way up here in my upper tail, really, really small. You might not even see it if I went to my calculator. So I added those 2 probabilities. This first one was 0.00757. Well, that's really pretty small, right? We knew this one was going to be even smaller than that, right? 0.00051. I added those together, and so the proportion of customers who can't fit in this neck size, 14 to 18, is really pretty small, right? It's less than 1%. That makes sense. That makes sense. I want to sell shirts to pretty much every male out there, and I want to sell a lot of shirts, and I'm trying to manufacture them so that they sell. So let's just go to the calculator, and I'll kind of show you where I got those numbers from. So I think I'm going to do my normal CDF again. So I'll just clear that out. Second vars, normal CDF. So I want something lower than 14, right? So I think I can just pretty much pick any number lower than, number lower than 14. So let's do a neck size of 10 or something like that. My upper here wants to be 14. Well, my mean we said was what? 15.7. My standard deviation was 0.7. And that's where I got that 0.00757. Really, really small number. Real quick, I'll do the same for my upper neck size. So normal CDF, I want to add up, accumulate. So in this case, my lower was 18. What's my upper going to be? You can pick pretty much any number you want, way above 18. You can pick 30, 20, 50, 5,000. It doesn't really matter. No one's going to have a neck size that big. So let's do 25. I have no idea what a neck size of 25 means, but it's probably a pretty big neck. The mean hasn't changed. The standard deviation hasn't changed. So we'll just go back to my home screen. And that's so small, the calculator doesn't even give me a decimal. It puts it in scientific notation. So all I did was add those two percentiles or probabilities, and we got a very small number. Makes sense. I want to sell shirts to pretty much everyone if I can. And so I got those two numbers from my calculator. We want you to use the calculator, but we also need to see your work here. So make sure that when you're going to the calculator, which we want you to do, we need to see some work, some backup, some supporting statistical work. And I'm sure your teachers have all been sort of saying that all year long. Show your work, show your work, show your work. Okay, part B says using a sketch of a normal curve, illustrate the proportion of men whose shirt sizes is medium. So again, I've tried to do my best to draw a normal curve here. There's my mean of 15.7. And I'm just eyeballing 16. I know that my standard deviation is 0.7, and so that's less than one standard deviation. So I've just eyeballed it. And my lower neck size to be medium was 15. So that's one standard deviation below the mean. So that was a little easier for me to eyeball, right? There's your sketch. That's it. A reader is going to look at something like, you know, your upper is greater than the mean, but we're not going to measure this. We're not going to get carried away with it. And we want this to kind of eyeball be around one standard deviation above the mean. But again, we're not going to spend a whole lot of time on your sketch. Quick sketch, show your information, and move on. So I want to know what's the probability between 15 and 16, right? Those are medium sizes, 15 to 16. So here's sort of my supporting work. But I think I'll go back to the calculator and try and get that number. I want to use the calculator effectively. I want to use it efficiently. And so I'm going to see if I can get that number relatively quickly. And again, I'm thinking, you know, just by eyeballing it, it's going to be 40, 50% or something like that. So back to normal CDF. Hopefully you've been using this all year. I want to know between 15 and 16, the mean hasn't changed, the standard deviation hasn't changed. Go back to my home screen. And it's about 51%. So one of the things that we find when we grade students' exams is many times they don't AP, they don't address the prompt, they don't answer the question we're asking. So in part B, it says use a sketch. There's my sketch. Illustrate the proportion of men whose size is medium. I've done that. Calculate this proportion. So many times we see one or the other, but you know, many students just, it seems like they forget to answer both of those. So before you move on to the next problem, just make sure that you really address the prompt, AP, right? And answered the question or questions we've asked. And here there were sort of two. And so sometimes I say to my kids, you know, underline both and make sure that you've addressed both of those. So it's a really nice problem. And I actually do like part C quite a bit. And I think we'll come back to that and just address it later when we're doing some probability. So that was from the 2003 exam. Here's another free response from the 2004 exam. Form B, years ago, the College Board would release two different exams. One was what we call the operational, one was what we call the international exam. Things have changed, and the College Board, it releases just one exam now. But so if you're seeing Form B, we used to release the two exams. When I say modified, it doesn't have parts C and D here, that's all. And those were not, excuse me, standardizing scores. So trains carrying bauxite ore from a mine in Canada to an aluminum processing plant in northern New York State in hopper cars. Okay, I envision a big railroad car train. Filling equipment is used to load ore into the hopper cars. Okay, car pulls in, they drop a bunch of bauxite ore into it, pulls forward, they keep doing it. I'm just envisioning in my own mind what's happening. When functioning properly, the actual weight of ore loaded into each car by a filling equipment at the mine are approximately normally distributed, that's good, with a mean of 70 tons and a standard deviation of 0.9 tons. So that's a pretty big standard deviation, right? Almost 1 ton. But when you think about it, you know, we're dumping bauxite ore into railroad cars. There's no way they all weigh exactly 70 tons. I know that for a fact. I'm just pretty convinced of that in my own mind. So they will vary, like everything in life. That's a big standard deviation in one respect, almost a ton. But you know, when we're putting in 70 tons, that's a lot of bauxite ore, and we know it's not going to be exact, and probably the filling mechanism has it down to a science, and it's probably relatively accurate, but we know it's going to vary, right? If the mean is greater than 70 tons, the loading mechanism is overfilling. Okay, if I own the bauxite ore company, I don't want to overfill all the cars. I would love it if every single car was exactly 70 tons. I don't want to go less than 70 tons because then my customers, you know, may get mad. And I don't really want to go way over. So they do say it's approximately normally distributed, and so that's good. Probably some of them will be 70 tons, and some of them will be more than 70 tons, and realistically, probably some of them will be a little less than 70 tons. And we just live with that in life. That's just life. So here's the same problem. So part A says, if the filling equipment is functioning properly, okay, 70 tons, what is the probability that the weight of ore in a randomly selected car will be 70.7 tons? So a little greater than 70 tons. Show your work. Always show your work whether we ask for it or not. So you know what I'm going to do, right? There's my attempt at my normal curve. My first row is tons of ore, tons of bauxite ore. The mean was 70 tons. Second row is Z-score. Third row, area, percentile, or probability. Again, they all sort of mean the same thing to me. At 70 tons, which is the mean, your Z-score is 0. You're in the 50th percentile. Again, just sort of helps my kids get into the problem. And you know, there's lots of numbers floating around here. So if I add one standard deviation above the mean, I'm at 70.9 tons. My Z-score is 1. I'm in the 84th percentile. Okay. Well, they told us what? We were at 70.7. So I know it's going to be less than one standard deviation above the mean. And I know that my percentile is going to be between 0.5 and 0.8413. So what's the probability that my Z-score is 70.7 minus 70 over 0.9? Let's go back to our calculator, see if we can type that in. So let's do normal seat second bars, normal CDF. I want to start at 70. No, let me just calculate the Z-score here. Sorry, I'm just going to calculate my Z-score here. So 70.7 minus 70. Well, that's 0.7. That's easy. I want to divide that by my standard deviation of 0.9. So I'm 0.777 standard deviations above the mean. We knew that one standard deviation was 0.9, right? So if I multiply that by 0.9, I get 70. So I'm at the 70th percentile here. Let me go back to my problem. I think I just lost you guys, unfortunately. Maybe I didn't. Okay, so what's the probability? 70.7 minus 0.9. I got 0.218. So that's going to happen around what, 22% of the time? That's not all that rare. That's going to happen roughly 1 in 4, 1 in 5 times. And so in part B, I think that's what they're asking me to do. Suppose the weight of ore in a randomly selected car is 70.7 tons. So we know that's going to happen fairly often, right? About 77% of the time. Shading above that's going to happen. That's my 0.218. That's the probability that I was greater than that. So that's around 22%. I don't think it's that rare, right? So that's 0.77, 22% of the time. Again, I don't think it's all that rare. And I think that's what they're asking for in Part B. So Part B says, suppose the weight of ore in a randomly selected car is 70.7 tons. Would that fact make you suspect that the loading mechanism is overfilling the cars? Justify your answer. Well, it's clearly 70.7 tons is clearly more than the 70 tons, but we know that it's going to vary, and they said that it's going to vary approximately normally distributed. So I would not suspect that the loading mechanism is overfilling the cars if a randomly selected car was filled with 70.7 tons. This would occur about 22% of the time, or about 22% of the cars would have 70.7 tons or more. So this would not be an unusual occurrence. So we know that it's going to, at times, overfill the cars, right? That 70.7 tons is going to happen around 22%. Again, I've just rounded this 0.218. We don't think that's that rare. We don't think that's that rare. So clearly at 70.7 tons, we have overfilled the car. But we know that we're putting in 70 tons and it's got a pretty big standard deviation. So we don't think it's that rare. So we're going to wind down here. I think I'm right around my 45 minutes. I think I had one more free response from the 2011 exam. I actually worked on the rubric team on this, and this was kind of interesting. We asked students to come up with some Z-scores in Part A. Someone's running the 40-yard dash, and we want to know what's the probability that they ran less than 4.4 seconds. And then in Part B, they were lifting some weight, and we wanted to know what was the probability that they lifted over 370 pounds. So let's do Part B real quick. I think I can squeeze it in. Strength is measured by the amount of weight lifted, with more weight indicating more desirable greater strength. What was a little confusing for kids was in Part A, we wanted them to run fast or smaller time was better. And in Part B, we want a higher or larger weight. From previous strength data for all players in this position, the amount of weight lifted has a mean of 310 pounds and a standard deviation of 25 pounds, shown in the table below. Calculate and interpret the Z-score for a player in this position who can lift a weight of 370 pounds. That's way more than I can lift. Perhaps some of you, if you're real athletic, maybe you can lift 370 pounds. That's way past my prime here. So again, I'm going to draw my little picture. I didn't draw the picture in Part B. I just found the Z-score. So 370 pounds was my score, minus the mean of 310 over standard deviation of 25. I got a Z-score of 2.4. So that was the first part, and they asked me to interpret it. So a player who can lift 370 pounds is 2.4 standard deviations above the mean. That's really strong. Yeah, most of us cannot lift that weight. So anyway, that's pretty much it for today. Let's kind of wind down and we'll call it a day. Luke will be back with you tomorrow. So hopefully by now you're more comfortable calculating, interpreting a standardized score. And in our class, or in this class, many times when we standardize, we look at what we call a Z-score. Hopefully by now you're saying to yourself, in all problems in AP statistics, you should be able to write a clear, concise solution in context. So we really want good communication, relate your answer to the problem that we are Always use context, and it's so valuable. And hopefully Luke is, I know Luke's saying the same thing. So your homework for tonight, Luke will post on his website. I think that's bivariate data. It looks like a least squares regression line or something, and we're asking you to interpret slope and context.